Hey there, and welcome to The Info Engineer. Okay, today we're diving into a seriously critical, high-stakes explainer. Look, if you're a forward-thinking construction leader, a developer or an engineer, you know we all absolutely obsess over what goes above ground, right? The glass, the steel, those beautiful architectural lines. But today, I'm going to show you why the true survival of literally any project is dictated entirely by the invisible forces below it. A pre-construction soil test is not just some annoying box to check on your paperwork. It is the foundational insurance policy for your entire investment.
Let's just dive right into this with a number that should honestly make every single project manager pause. $15 billion. In the US alone, expansive soils cause over $15 billion in annual damage to buildings and infrastructure. To put that completely mind-boggling number into perspective, in a typical year, these invisible shifting forces in the soil actually cause a greater financial loss to property owners than earthquakes, floods, hurricanes, and tornadoes combined. It is a massive, completely silent threat.
So here is our game plan for this explainer. 1. The invisible geotechnical risk. 2. Catastrophic real-world consequences. 3. Vital engineering soil essentials. And 4. The brutal financial reality.
All right, let's jump straight into Part 1, the invisible geotechnical risk.
When we map out the terrifying global distribution of shrink-swell soils, the sheer scale of the problem becomes super obvious. We are talking about massive problem areas across the Americas, Africa, Europe, Asia, and Australia. This proves that this invisible risk isn't just some rare local anomaly that you can brush off. No way. It's a worldwide threat. Whether you're breaking ground in Texas, the UK, or China, the ground beneath you might literally be a ticking time bomb if it isn't properly assessed.
So, what are we actually dealing with here? Well, expansive soils are packed with specific clay minerals like smectite or vermiculite. And when these clays absorb water, they act exactly like a giant sponge. They swell up, causing ground heave, and can actually increase in volume by up to 10%. But then, when they dry out, they shrink back down and become incredibly hard. This constant, relentless heaving and shrinking is what silently tears shallow foundations and pavements apart. Get this, just a 3% change in volume expansion is more than enough to severely damage a structure.
Moving on to Section 2, catastrophic real-world consequences. Let's look at the hard evidence.
This specific residential failure perfectly illustrates a phenomenon we call end lift. This happens when the soil swells unevenly around the outside edges of a building, but the center of the foundation basically stays put. Those swelling pressures are so incredibly powerful that they literally rip right through brick, mortar, and concrete. This specific type of differential settlement is so destructive, it costs the UK insurance industry an estimated £400 million every single year.
Now, the danger compounds super fast when we introduce external factors into the mix, like trees. Every tree has a zone of influence where its roots spread out, and roots, well, they actively hunt for moisture. They create massive localized changes in the soil's water content. So if your shallow foundation happens to sit within that zone of influence, the tree is essentially sucking the water out of the expansive clay right under your building. This causes severe, localized shrinkage and differential settlement. It completely alters the soil profile and just wrecks the foundation.
But hey, this isn't just about small residential homes. Let's talk about one of the absolute most catastrophic case studies in modern geotechnical engineering, the 2009 Shanghai building collapse. We are talking about an entire 13-story high-rise that abruptly toppled over, entirely intact, completely flat onto the ground. Why? Simply because the subgrade conditions and the staging of the earthworks were completely ignored and mishandled.
Here is the forensic timeline of that disaster, and it's basically a nightmare scenario. First, the developers placed a massive 10-meter-high mountain of soil right next to the building. Then, a heavy 5-hour rainstorm rolled in, dropping almost 24 millimeters of water, fully saturating the topsoil crust. This triggered what we call an undrained general shear failure of the subgrade beneath that massive stockpile. The soil forcefully thrust upward against the building's basement, delivering this unbelievable impact force that violently snapped the 33-meter-long foundation piles in tension. The entire building fell southward in mere seconds. And the craziest part? All of this was entirely preventable with a standard geotechnical analysis of the temporary earthworks.
Or how about this stark example from Malaysia? Developers were rushing to finish a nearly 11-acre housing project. They bypassed local authority oversight, completely skipped vital physical soil condition advice, improperly compacted the earth, and built incredibly fast without allowing the soil to naturally settle. The end result? Block 5 of the development sank a staggering 5 feet straight into the ground. Obviously, this caused extensive structural damage and massive basement flooding.
All right, let's get into the science with Section 3, Vital Engineering Soil Essentials.
Like I said, these multi-million-dollar disasters are entirely preventable with proper testing. So, what does a comprehensive soil report actually tell your engineer? Well, we look at the exact soil type and clay mineralogy to predict its shrink-swell potential. We map out the critical water table level, which dictates buoyancy and moisture shifts. We assess the area's seismic profile so we know how vibrations might liquefy or shift the ground. And finally, we rigorously test the undrained versus drained strength of the soil. All of this highly specific data comes together to establish your project's ultimate bearing capacity.
Now, a really crucial takeaway here is understanding something called the active zone. This is the near-surface layer of the ground, usually the top 3 meters or so, where all of these crazy moisture and volume changes happen because of rainfall, droughts, or vegetation. If your project utilizes shallow foundations, guess what? They are sitting right inside this highly volatile active zone. Without knowing the exact properties of this layer, you are quite literally building blindfolded.
Which brings us to our final part, Section 4, the brutal financial reality.
So, here is my ultimatum as an engineering consultant. You have to compare the microscopic cost of a comprehensive Phase 2 soil report, which, by the way, is just a tiny fraction of your total project budget, against the downright apocalyptic costs of failure. We're talking astronomical fees for emergency underpinning, years of draining legal litigation, massive remedial repairs, or worse, total structural loss like we saw in Shanghai. A pre-construction soil test is not some bureaucratic regulatory burden. It is absolutely the most cost-effective foundation insurance policy you will ever buy in your life.
So, I'm going to leave you with this final provocative thought. As a forward-thinking construction leader, I want you to look at your next project and ask yourself, are you building on solid data, or are you just gambling your entire investment on a $15 billion blind spot? Remember, the ground beneath you is alive. It moves and it breathes. Make sure you know exactly what it's going to do before you pour a single drop of concrete. Thank you so much for joining me here on the Info Engineer for this explainer. See you next time.